Welcome, curious minds, to another deep dive. We live in this incredible era of language models, right? They're transforming everything from how we write emails to how we search for information, often showing, mind-blowing accuracy on so many tasks. But there's always a catch, isn't there? The sheer computational power and memory these massive models demand, well, it can be a real bottleneck, especially when you're asking them to handle really long conversations, analyze vast documents, or perform complex multi-step reasoning. It often feels like we're constantly trading off raw intelligence for practical, real-world usability. Today, we're peeling back the layers on something truly innovative that's addressing this head-on. Jet-Nemotron. This isn't just another incremental improvement. It's a new family of language models designed to really shatter that old trade-off between power and practicality. Our mission for this deep dive is to understand how Jet-Nemotron manages to match or even exceed the accuracy of leading full-attention models while dramatically boosting their generation speed. Get ready for some serious aha moments, because this could fundamentally change how we all interact with advanced AI.
Indeed, that efficiency challenge is paramount. For years, we've seen the brilliance of standard full-attention mechanisms in LLMs. They allow models to weigh the importance of every word in relation to every other word, which is fantastic for understanding context and achieving high accuracy. But yeah, this comes at a significant cost. A quadratic computational complexity, often denoted as ON2, where n is the length of the input sequence. What that means in plain terms is that if you double the length of your text, the computational effort doesn't just double, it quadruples.
Wow, quadruples. That scales badly.
Exactly. And this explosive growth also creates a massive key value cache, the KV cache, that devours memory. It becomes a major bottleneck, especially with long prompts or generated responses. So many solutions have tried to address this, leaning into linear attention with its much more efficient ON complexity, where doubling the text only doubles the compute, or trying various hybrid models. But almost without fail, these solutions came with a noticeable drop in accuracy, especially on demanding benchmarks like MMLU or mathematical reasoning. What's truly fascinating here is how Jet-Nemotron seems to sidestep that compromise entirely, offering, well, the best of both worlds.
So the big claim here is that Jet-Nemotron isn't just a little bit faster, it's significantly faster without sacrificing intelligence. Can you give us some of the headline figures that make this so exciting? Because significantly can mean a lot of things.
Absolutely, and these aren't minor tweaks. The Jet-Nemotron 2B model, for instance, achieves comparable or even superior accuracy to well-established, powerful models like Qwen 3, Qwen 2.5, Gemma 3, and Llama 3.2 across a wide range of benchmarks. But here's where it truly shines. It delivers an astounding up to 53.6 times generation throughput speedup and a 6.1 times prefilling speedup compared to leading models like Qwen 3 1.7b base.
53 times.
Yes, and these numbers are particularly evident in long context scenarios, like processing up to 256,000 tokens. Imagine analyzing a whole book in seconds.
53 times faster. That's not just an improvement, that's a paradigm shift. Imagine the real-world applications for you, the listener. Longer, more coherent conversations with AI that don't lose context, complex document analysis in seconds instead of minutes, or even running truly powerful LLMs on less powerful hardware, like edge devices, without major performance hits. This truly sounds like magic. Okay, let's unpack this. How do they achieve such a leap? What's the secret sauce behind this kind of architectural breakthrough?
The breakthrough is rooted in a novel methodology called post-neural architecture search, or PostNAS. It's truly a revolution in how we design these complex models because it flips the traditional approach on its head.
Before we dive into PostNAS itself, you mentioned freezing the MLP weights. For listeners who might need a quick refresher, what exactly is the multi-layer perceptron's role in a standard LLM, and why is it so significant that they chose to freeze it?
That's a great question because it's key to understanding PostNAS's efficiency. In an LLM, you have the attention mechanism, which is excellent at identifying relationships between words.
Right.
But after that, the MLP layers are essentially the model's deep thought processors. They take the information from the attention layers and transform it into a richer, more complex representation. They're where a lot of the model's core knowledge and reason capabilities reside.
Okay, the reasoning part.
Yeah.
Got it.
Now, traditional architecture search often means starting from scratch, trying to design both the attention and MLP layers simultaneously. This is incredibly costly and, frankly, risky. PostNAS takes a unique and highly efficient path. It begins with a pre-trained full attention model and freezes its multi-layer perceptron MLP weights. This is a brilliant insight because it means they're not reinventing the wheel with every new architecture search. They're preserving the core knowledge, the reasoning capabilities the model already has, allowing them to focus all their computational power on optimizing just the attention mechanism, the real bottleneck for efficiency, without having to retrain the entire brain of the model.
Ah, I see. So it's like tuning the engine without rebuilding the whole car.
Exactly. It's a monumental saving in time and resources, making advanced LM architecture design much more accessible.
That makes so much sense. So no more starting from absolute scratch, which sounds like a huge relief for anyone who's ever faced that blank page in design. So how does this PostNAS methodology pull off this architectural magic? It's not just one silver bullet, is it?
Precisely. It's not one solution, but rather a brilliant orchestration of 4 key innovations working in harmony within the PostNAS pipeline. Let's peel back the layers and start with a strategy that might seem a little counterintuitive at first: strategically keeping some of those full attention layers.
Right. It does seem counterintuitive to keep full attention layers if they're so computationally hungry. What's the strategy here? Are they just sprinkled throughout the model?
This raises an important question, and it's where the first innovation, full attention placement and elimination, comes in. While full attention is computationally intensive, a few well-placed full attention layers are absolutely essential for maintaining high accuracy on challenging tasks, especially things like document retrieval, where precise connections across long distances are critical.
Okay, so quality over quantity for those layers.
Exactly. The innovation here is an automatic method that learns the optimal placement of these layers, rather than just distributing them uniformly, which is the common, less efficient strategy. They train a once-for-all super network and then use beam search to identify exactly where to put them. For those unfamiliar, beam search is a clever way to systematically explore many possible configurations without checking every single one. It quickly homes in on the best designs for layer placement, much like a focused searchlight rather than a random scatter. What's fascinating here is a truly subtle but powerful insight. They found that not all attention layers contribute equally to all tasks. For instance, only maybe 2 or 3 layers might be critical for MMLU accuracy or for retrieval tasks. MMLU, by the way, stands for Massive Multitask Language. Understanding, think of it as a comprehensive IQ test for language models, covering everything from history to law to computer science, making it a true test of a model's broad intelligence and reasoning.
Right, tough benchmark.
Very tough. And crucially, the layers important for MMLU aren't necessarily the same ones important for retrieval. This task-specific importance means Jet-Nemotron can surgically apply the most expensive computational resources only where they're absolutely critical, rather than wasting them everywhere.
That's brilliant. So instead of a blunt instrument, they're using a surgical scalpel, only applying the heavy-duty full attention exactly where it's needed for peak performance. That takes care of the critical, high-impact areas. But you mentioned most of the layers would use linear attention. How do they decide which type of linear attention to use for the remaining bulk of the model?
That brings us to the second pillar of PostNAS linear attention block selection. Once we know where the crucial full attention layers go, the next step is to systematically evaluate and select the best existing linear attention blocks for the remaining layers. Because the PostNAS framework has those low training costs we discussed, they can rigorously test various state-of-the-art linear attention blocks. We're talking about cutting-edge approaches like RWKV7, RetNet, Mamba2, and gated DeltaNet.
Okay, so they test the leading candidates.
Exactly. And after extensive evaluation, they found that gated DeltaNet achieved the best overall accuracy. This is due to its clever combination of a data-dependent gating mechanism, which is like having a smart filter that dynamically decides how much attention to pay to the current input versus the ongoing history, ensuring the model's focus is always optimally placed. And it then uses the delta rule, which efficiently updates memory with new information, helping to conserve that limited state memory crucial for long contexts.
So they've identified where to put the powerful full attention and which of the best existing linear attention blocks to use for the rest. But what if the team believed they could push the boundaries even further? Did they stop there, or did they actually innovate on the linear attention block design itself?
You're hitting on the third innovation, new attention block design, which introduces JetBlock. Precisely. They didn't just pick from the best. They developed a novel linear attention block within the PostNAS framework to further enhance the model's expressive power. Traditional linear attention blocks often use static convolution kernels. meaning they have a fixed lens they always use to analyze information. They can't adapt their feature extraction patterns based on the unique characteristics of the input.
A fixed lens.
Okay. JetBlock solves this by introducing a kernel generator module that dynamically produces convolution kernels based on the input features. Think of it like this. Instead of the model having a fixed lens it always uses, the kernel generator module allows the model to craft the perfect, customized lens on the fly for each specific piece of input.
Adaptive.
Very adaptive. It makes its feature extraction much more adaptable and powerful. These dynamic kernels are then applied to the value V tokens, and they even found they could remove redundant static convolutions on the query Q and key K tokens with negligible impact on accuracy, streamlining computation even further. JetBlock consistently delivered significant accuracy improvements over prior linear attention blocks, especially on math, reasoning, and retrieval tasks, showing that custom design can push the boundaries even further.
So they've not only intelligently placed full attention and selected the best existing linear options, but also invented a superior one with JetBlock. And all of this is then optimized with an eye towards the final application, right? Which brings us to the fourth component, the hardware-aware search. This sounds like the real-world performance optimization. It's not just about theoretical parameters, but how it runs on actual chips.
Exactly. This final component, hardware-aware architecture search, is critical for practical deployment. Traditionally, designers might focus on minimizing parameter count as a proxy for efficiency. But this doesn't always translate to real-world hardware speed or energy consumption. PostNAS takes a hardware-aware approach, using generation throughput as a direct target for optimizing architectural hyperparameters like key value dimensions and the number of attention heads.
So targeting speed directly.
Directly. And if we connect this to the bigger picture, a crucial finding here is that KV cache size is the most critical factor influencing long context and long generation throughput. Let me explain why. Decoding, the process of generating new tokens, is often memory bandwidth bound.
Meaning it's limited by memory speed.
Precisely. The speed is limited by how quickly data can be moved from memory to the processing unit, not just by how fast calculations are done. In long context scenarios, the KV cache, which stores the keys and values needed for attention, can actually consume more memory than the model's weights themselves. By reducing its size, you dramatically decrease memory transfer time per decoding step, enabling larger batch sizes and fundamentally improving throughput. PostNAS optimizes these configurations to maximize accuracy while intelligently managing the KD cache size, which is a true game changer for practical deployment on diverse hardware.
So Jet-Nemotron combines all these innovations, the strategic full attention, the meticulously selected linear attention, the dynamically adaptable JetBlock, and the hardware-aware optimization for that crucial KV cache.
Right.
What do the overall results look like across the various tasks we care about?
The empirical results are truly compelling. Jet-Nemotron 2B and Jet-Nemotron 4B not only perform comparably with, or even better than, leading full attention models across all 6 evaluation domains. That's MMLU-Pro, mathematical reasoning, common sense, retrieval, coding, and long context tasks, but they do so with dramatically higher efficiency. For example, on MMLU-Pro, Jet-Nemotron 2B achieved higher accuracy than Qwen 3 1.7B base while being 47 times faster.
47 times. Still amazing.
It is. It even outperformed more massive mixture of experts, or MOE, models like DeepSeek v3 Small. MOE models, for those unfamiliar, like having a team of specialists. They have a very large total number of parameters. DeepSeek v3 Small has 15 billion, but only a few are activated for any given task, around 2.2 billion for DeepSeek. Despite this architectural advantage, Jet-Nemotron, with its much smaller scale, still came out on top. And in long context tasks, Jet-Nemotron 2B delivered that remarkable 6.14x prefilling speedup and a 53.6x decoding speedup compared to Qwen 3 1.7B base at a 256K context length. This substantially pushes the boundaries of the efficiency-accuracy trade-off, showing that you really don't have to compromise anymore.
That's truly groundbreaking. It means we don't have to choose between a smart model and a fast model anymore. But for every breakthrough, there are often trade-offs. Are there any scenarios where this incredible efficiency might come with any compromise, even a minor one, compared to a pure, full-attention behemoth?
That's an excellent point to consider. While Jet-Nemotron excels across the board, the paper suggests that the trade-off is virtually eliminated across most benchmarks. The cleverness of PostNAS is precisely in identifying where full attention is indispensable and using it sparingly, making the compromise negligible. Its strength is in avoiding that choice altogether.
Okay, so they've really engineered around that potential issue.
It seems so. For you, the listener, whether you're developing applications, researching, or just using AI tools, this has immense practical benefits. It promises faster, more responsive, and more cost-effective AI experiences even on less powerful hardware like the NVIDIA Jetson-Orin, where Jet-Nemotron 2B showed an 8.84x speedup over Qwen 2.5 1.5B. This makes powerful AI far more accessible.
Today, we've taken a deep dive into Jet-Nemotron and the groundbreaking PostNAS pipeline. We've seen how this brilliant methodology intelligently combines strategic full-attention layer placement, meticulous linear attention block selection, novel dynamic convolution with JetBlock, and hardware-aware optimization for that critical KV cache size. The results: models that are both incredibly accurate and astonishingly fast, all thanks to a systematic approach that optimizes existing powerful components rather than always starting from scratch.
This raises an important question for you to ponder. How might this paradigm shift in architecture design? Moving away from the costly and time-consuming from-scratch training and towards optimizing existing powerful models. How might this accelerate the democratization of cutting-edge AI? Could this make advanced LLMs accessible on more diverse hardware, from mobile devices to large-scale data centers at significantly lower operational costs? Could it truly transform applications across the board?
Something profound to chew on as the future of AI unfolds. Thank you for joining us on this deep dive.
Bye.
Until next time, keep exploring, keep questioning, and stay well informed.